Okay, we are live. Good. Hello, everyone. This is Postgres TV Open Talks series. I'm Nikolai, my co-host Ilya. Hi, Ilya.
Hi, everyone.
As usual, as a reminder, we invite the best of the best speakers from Postgres, popular Postgres conferences. And today our guest is Oleksii Kliukin. Hello. Thank you. Thank you for coming. Thank you for coming. And we will talk about Kubernetes plus Postgres today, right? You currently work at Timescale, but before that you worked in, correct me if I'm wrong, at Adjust and at Zalando, right? And I think you are one of those people in the Postgres community who have great experience with Kubernetes.
And who actually almost started this thing for Postgres.
At Zalando, right? Many years
you were
ago.
one of the first people who ever bothered to try Kubernetes for Postgres, as far as I remember.
Right?
Yeah, we found all the problems pretty early.
Yeah, right. Like out of memory and so on, right? Okay, good. Absolutely. So great. I'm very happy that you agreed to redo this talk, which was not recorded, as I understand, but actually it doesn't matter. We can redo it. Even the talk is recorded, we can still redo it. But before we start, let me remind our rules. We usually say we don't have limits in terms of time, but Ilya says let's keep 1 hour. It's up to you actually, but maybe let's not use 2 hours of our time. But if topic is interesting, we can definitely extend. We will be asking questions at any time.
We would be mocking your audience, so we will try to make this a vivid conference talk, if we can.
Right. Yeah, I thank everyone who delivers feedback in any form for us, in form of comments, participation in chat. We have several viewers right now. Unfortunately, only few as usual. Most people watch us recorded, but those who joined us online, they have opportunity to ask questions, and we will be monitoring the chat and deliver questions to Oleksii. So that's actually it. As usual, 1 second of time for those who didn't subscribe yet. More than 50%. This is not fair, as I've said. Please subscribe because we have a lot of interesting content. We bring a lot of interesting people all the time. If you're interested in Postgres, this is the right place to subscribe and participate. And of course, you can request some topics to be covered, some speakers to be invited. Please do it. It's easy to contact us and we listen all the time. Thank you. And of course, share this video with your colleagues in social networks, in working groups, Slack, and others like Telegram, Discord, what you have, just to extend their knowledge in this interesting topic. Okay, that's it. Let's start. Please share the screen.
Thank you. Sharing the screen.
Yeah, and I can see it. Good.
Mm-hmm. Amazing. So thank you, Nick. Thank you, Ilya, for the opportunity. My name is Oleksii Kliukin. I work at Timescale, and I've been working with Kubernetes for quite a while, since 2017, in another company. So the subject of my talk today is how we run a managed service on Kubernetes and Postgres at Timescale, and specifically what we learned, which challenges we came across, and how we resolve these challenges. I want to first touch on briefly what is Timescale and what is our relation to the Postgres community, and how did we end up running databases on Kubernetes at scale. So Timescale is a database company that extends Postgres with capabilities to store and analyze time series in an efficient way. We provide an extension. The extension is free and open. And among other things, that extension improves, adds to the concept of normal Postgres tables, the special abstraction that is called a hypertable. A hypertable is looks like a Postgres table. You can query it, you can add data to it, but in the background, we partition that table. We call those partitions chunks based on some user-specified metrics. For instance, every 6 hours or every 10,000 IDs. For that, we need a column that represents time, not necessarily a time column. It could be also a column that is that behaves like time, which is it constantly increments. For instance, a serial column, an ID, and those partitions that we call chunks are separate tables, so they avoid the problem of running Postgres with extra large tables, such as tool on vacuum, or even potential wraparounds, or queries or data that doesn't fit, indexes that don't fit in memory. And we not only provide those ways of partitioning your table in the background, so you don't have to create new partitions, we just create it for you when you insert new data. We also provide a way to query that table in an efficient way, because we extend the Postgres planner so that it only goes to relevant partitions. That is actually similar to what we have in the recent Postgres versions with the stop partitions. We also don't only limit ourselves to one node, to one Postgres server, but we can make this hypertable distributed, meaning that the partitions, chunks, may reside on different Postgres servers. And what we do is we designate a single server as the so-called access node. The access node receives queries, and then it transparently directs those queries to one or more data nodes containing actual data, and gathers the results and delivers it back to the user. Not only it works for select queries, it also works for data changes, and data changes are performed in a consistent way. So, the same guarantees as you have with a single Postgres server, that atomicity, consistency, isolation, and durability. This is also happens with hypertables as well. So, well, you can store data. You can store time series data in an efficient way. You can store huge amount of time series data, but what you actually need it for, you need it for querying. And we provide some capabilities there as well. We provide aggregates so that you can make sense of your data in analytics. We also provide abstractions that are called real-time aggregates. They basically behave like materialized views, only unlike materialized views, they are refreshed automatically, not just from data that is stored in the tables, but also from very recent data. And we provide data retention policies. So if you have a lot of data, a lot of your time series data, say for compliance reasons, you have to store it for 5 years, you can set a policy that says everything that is older than 5 years has to be deleted. One of the biggest problems with huge databases is you have to know when to delete your data, because otherwise you will just run out of disk space, memory, and so on. There's also transparent compression. You can compress your data, and that data could be also queried while being compressed, and our compression is pretty good. So it could give you 10 times gain over the uncompressed data. We go great length to make sure that queries are performed adequately. We provide a lot of improvements. For instance, queries that use index, some aggregate queries, like if you want to find the maximum of your data, we will make sure that you don't go to every partition, but you will only go to relevant partitions, because we know that your data is sorted because it's time series data. We can take advantage of that to make queries more efficient. So that is all about Timescale, and we provide also a Timescale cloud. So you can run Timescale as an extension on your own system, on your laptop, on your production server, and that is free, that is open. You can look at the source code, you can modify the source code, you can contribute your modifications, you can run your modifications. And we provide you a way of doing this. We provide you a way of running Timescale in a couple of clicks. That is a Timescale cloud. So this is the subject of my talk, but I will not cover the user side of Timescale cloud, how to use it. It's pretty simple. I will talk about the architecture first. How did we design Timescale cloud? Why did we decide to use Kubernetes for that? Then we come straight to challenges. So what happens if you run your databases at scale on Kubernetes? What could possibly go wrong? And there are quite a few things that could go unexpectedly. And last, I think it's quite important that we'll tell about our developer experience. That is experience of ourselves, people who develop cloud. How do we make sure that the software we develop are reliable? How do we make sure that we don't accidentally roll some untested changes to production? How do we test things? And how do we deploy things? So let's start straight to Timescale Cloud. I will show a couple of screens first. This is how it looks like. It's cloud.timescale.com. We have databases here. Each database is called service in our terminology. I know this is confusing, but in Postgres, everything that represents a database is quite confusing. If you say cluster, and you have Kubernetes clusters, Postgres clusters, availability clusters, and also cluster is a command in Postgres. So service is not such a bad name. And here you can see that we have some services running. One service is post, which means it has disk with the data, but it doesn't have any compute and memory. You don't pay for it. And this is the deployment screen. You can choose either you want a single node, which is just a single Postgres server running your hypertables, or you want us to set up a multi-node, which consists of multiple servers and allows you to run distributed hypertables. As a name, we provide several regions. You can set up your compute and disk size. Compute is actually not shown here because it's scheduled by the region. And there is a price. Yeah.
Regions are in AWS, right? I mean, only everything is in AWS. Okay.
That's good. I will go straight to it there. We are running on AWS, so we use AWS regions. We are not limited in architecture to run only on AWS, but so far AWS is something that we focus on to provide the best experience.
Yeah,
there's also pricing. Yeah.
Also,
yeah,
maybe off topic, but I always wonder, does it make sense to consider some kind of like hybrid approach when you, for example, you run Postgres yourself, some databases, or use RDS, but you need a good time series, and so you also consider Timescale Cloud. Should I like move everything to Timescale Cloud, or it's okay to run multiple services in different places? Like this question always bothered me, I would say, right? So
yeah, I think we have customers that run some of their data on premises or in their own accounts, and some data in Timescale Cloud. Particularly for time series data, it makes sense to run it in Timescale Cloud. And then, for instance, if you aggregate your data and then query the aggregated data, there are not so many data at the end of the day compared to the raw one. So you can combine it with something else from the application.
Thanks.
All right. So there is also pricing, and you can have a 30-day trial if you just want to try Timescale or try to our cloud. You can go there and have a 30-day trial and pay nothing. And then at the end of the day, we don't ask for the credit card, so you can decide not to continue, or if you like it, you can continue with that. So I just wanted to show how this looks like from the user perspective. When you create, you get a connection string, you get a password. The password is not shown here. And you can immediately, once the server is running, you can immediately use that connection string to connect and run your queries. We provide some test data. We provide some test queries, and we also provide demo instances that contain test data. So you can use it if you just want to play with Timescale without loading your data into the account. And that is how the running server looks like. Again, there is a service URL. It doesn't contain a password. If you did not write your password during the deployment, you can reset it, but we won't store it, and we won't show you again here in the UI for security reasons. There is a configuration, the CPU, RAM, disk storage. I will also show this configuration in a bit different context soon. There is a region where it's running. And you can also see this says forked, which means that we kind of created a copy of another service by forking it. I will also come to that a bit sooner, a bit later. Sorry. So this is let's actually talk about how this works. And with Kubernetes, there is AWS. 5 years ago, when I was delivering talks about Kubernetes, I've been spelling out all the Kubernetes primitives: what is pod, what is node, what is service. I don't believe that this time it's necessary. I think a lot of people are familiar with Kubernetes, especially people who come to talks like that. Just to mention that there are kind of two schools of thoughts to map Kubernetes to your traditional understanding of how computing works. One just says that you have nodes, you have pods, that's your servers on premises, you have services of Kubernetes, that's your load balancers, you have config maps, that's your ini files, and so on. Another school of thought basically tells that Kubernetes is a distributed operating system. So look at your containers, this is the application, look at your pods, those are kind of application groups, look at your load balance, look at your services, those are sockets, and so on. So whatever abstraction you choose, that is fine. That kind of describes Kubernetes as a way of orchestrating multiple containers and providing a way of deploying and running those containers, providing an easy way to monitor those, and allowing you to declare what you want using YAML. YAML is not the best declaration out of there, but it's definitely better than JSON for writing, and it's acceptable, so to say. But since Kubernetes is an container orchestration, I think it's worth staying on the topic of why would you like to run Postgres in a container? And I've met a lot of people that says, hey, you're crazy. You don't know what's happening in the operating system, and now you have another abstraction of the container that's going to be crazy. That's going to be a mess. And possibly, we at Zalando started running Postgres in containers in 2013 or 14. Those were Oleksii containers, and long before Docker. But the idea is roughly the same. One thing that the container provides you is making sure that you run exactly the same set of binaries and configuration files everywhere. So here is your test instance, here is your production instance. You don't have a drift of Postgres versions or Postgres configuration or anything or extensions. It's exactly the same. You can test it on your laptop. You can deploy it to the cloud. There are some downsides to that because it's not easy to change the contents of that container without restarting the pod. But this is a very strong pro for me for containers. It provides some predictability. Then there is a basically idea of slicing your servers to multiple Postgres installations without collocating them. If you ran several Postgres versions on a single host, you know there are multiple things that can go wrong. They compete for shared memory. They start to use the same ports, and you have to reconfigure them. A single Postgres installation that goes bonkers can also kill the whole instance, especially if it's under heavy load, and other Postgres installations on the same host can also go bad. If you have HA, then one of your instance may fail over and become a replica while the other is running the primary. And then it's really hard to deal with that without accidentally stopping another primary. So yeah, I've seen that, and slicing the host into containers and then operating each container as it were an independent server is actually much better than this collocating approach. And last but not least, in a container, you have a separation between your binaries, which goes with the Docker image and with the Docker operating system, with the Docker file system, and an external volume where you store your PG data. If you want to store your PG data on a container file system, please don't. It's a layered file system that grows when basically creates a new layer when you write new data. It's not performant, but probably is not reliable for Postgres case for Postgres considerations. So people typically mount a volume and run your PG data on an external volume, and that is what we do, and that is also what most people do. And that means that you can restart your container and your data are completely intact somewhere else on the volume, maybe even on the network file system. So even if your whole host where the container is goes down, you still have your data untouched. So,
if you talk about pros and cons of running Postgres in a container, I have a question.
Sure.
For example, if we have Ubuntu 16.04 running with Postgres, Ubuntu 16.04 is already end of life. It's already old. And so infrastructure team decided to upgrade all Ubuntus, but didn't talk to DBAs, DBREs, and there is a problem because like it's silent glibc version change, leading to index corruption very easily. If nobody, it's easy to get into this situation and understand it only when it happened and users started to complain some search is not working and so on. Don't you think that running Postgres in container increases the chances of this? As you said, we just mount PG data directory. We can have different glibc version, right? I mean, not expected, and they cannot the situation that version of glibc we have doesn't match PG data, and nobody tells us. Postgres won't complain. Don't you think the practice of running Postgres in container increases chances of it?
I think this is fair. That it could lead to binaries being upgraded silently without the data staying the same. Ironically, I've seen this glibc problem twice. One when running Postgres in container, and another when running Postgres on premises. So I don't think this is very specific to the container. It depends on who actually creates your container. If you just take a container from someone else, you don't look at either a changelog or what is inside and just use it, and then let this container be silently upgraded, you're up for troubles. Probably not just glibc, but all other sort of troubles.
So don't use a container image from a stranger, right? So use your own
solution. Don't trust your data with some binaries from the internet. Always verify those binaries. And in our case, and basically everyone who runs a database as a service probably builds their own containers, because you typically have your specific requirements. For instance, the set of extensions that you want to run. You want to control a Postgres version.
Locales.
Yes. Yeah. And chaos as well. Coming to glibc, you also want to control glibc. And you can even change the underlying operating system from the container. For instance, we had to do this once because glibc on our previous one was not new enough for some of our experiments. And PG data just stays the same. And it was, well, we obviously looked at the changelog and for glibc to verify that the data is not affected, and we tested things. But if you control your own, if you build your own containers, then you are in control of your destiny the same way as if you are running servers on premise. If you take binaries from the internet, and you don't look into those binaries, please don't do that.
This is the real problem, because there is so-called official Postgres containers in Docker or Moby repository on GitHub, and most people just use them, and they don't care about glibc version, right? And this is a problem, because it's easy to take just them and start using, and then upgrade, switch to different image, keeping PG data as is.
Actually, it's a very difficult question if people who actually use seriously large installations on Kubernetes using default official containers.
I agree. Well, yes, I agree. But people who just decide to use Postgres in Docker, for example, they will take this so-called official image. And then they can have trouble when this image changes, but PG data remains the same. This is my point. So it's like my point is actually, I think Postgres should control it and complain, but there is no such mechanism. Maybe it was developed for newer Postgres 15. I don't remember. I remember some discussion about it, but it's a big problem worth noticing. And like, I agree that it's not a containers and not containerization problem, but just maybe Postgres problem itself. Okay, sorry for off topic once again. Just things that disturb a lot.
That's appreciated. And as my colleagues, one of my former colleagues says, just always use Silvergale, and you don't have that problem. You have a lot of other problems, but not the problem with data corruption. Anyway, excuse me. Let's go further. So you run Postgres in a container, but now we have a host service, and that setup that we have some complexity, and I want to touch base on that. We run our cloud with microservices from the developer perspective. So we have microservices to deploy things. We have microservices to interact with the UI. We have microservices that do billing and some other tasks that is quite common. And there are a lot of advantages to splitting your workload and microservices. And Kubernetes arguably is designed exactly for running microservices, not big monolithic applications. Microservices are on top of Kubernetes, and services, basically our Postgres timescale installations, are also running on top of Kubernetes. Then we have Docker containers that Kubernetes manage. So this is like a third layer of complexity. And all of this runs on Amazon AWS, and Amazon AWS interacts with Kubernetes, sometimes in a very, I would say, mysterious ways. And there could be bugs in any of those layers. And I will also describe some of those bugs further. But you have to understand that when you run an installation like that in the cloud and Kubernetes using Postgres containers, you have to have some understanding of how things work on all of those layers. This is not just take it, run your production workload on it, and hope for the best. Hope is a bad strategy in that regard. You have to understand how Kubernetes works. You have to understand what are the downsides of running Postgres in a Docker, what could be wrong. And you also have to be proficient with AWS. Ideally, if something goes wrong, you have to find someone to fix things or complain about. You have to understand AWS limits so that when you try to deploy and then it says request limit exceeded, you are not panicking, but trying to know what to do with that. So all of that is kind of a complexity layers. And basically, this doesn't this convenience of running things in Kubernetes in the cloud in a Docker container is not for free. This is what you pay for, these complexity things. But on the bright side, it gives you almost infinite scalability as long as you can pay for it, because AWS can give you new instances instantly. With Docker, I already told that you have a predictable image that you run, and you can basically change your server as long as your volume is intact without affecting your product, without losing your data. And with Kubernetes, you have a lot of powerful APIs to deploy your applications, to monitor to change your react to changes in your applications. And also there are a lot of prepackaged tools like monitoring, for instance, that are specifically designed for Kubernetes. So you can download Helm charts from the internet. Also, disclaimer, don't download random binaries from the internet, always verify what are there. But you can also use something like Kind to run things locally and test it before you have things in the cloud. Also, what Kubernetes actually gives you is the ability to run things on AWS and at the same time test things on your laptop in a very similar environment. I've shown before how the service looks here in the UI. This is configuration. And this is our timescale custom resource definition. Essentially, we provide a YAML schema to describe every important aspects of your database. Now here, we don't have the whole YAML. It's quite big, but we have a brief description of it. This is kubectl, a Kubernetes client that allows you to query things or change things in Kubernetes. So you can see also that we have volume size, we have a CPU, we have sorry, this is CPU, this is memory, this is CPU, and this is volume. There is a flag that says whether we want to do backup or not. And this is a multi-node. So there are nodes in this service. This is how it looks like from the description, from the perspective of someone who operates Kubernetes. And this is how it looks like from the architecture perspective. Excuse me. So this is the Timescale custom resource, a YAML file describing your database. We use something that is called an operator pattern. An operator pattern takes your YAML file and converts it into Kubernetes primitives, not only when it is deployed, but also when it is changed. The process is called reconciliation, and the whole thing is called the operator pattern. The operator is typically how you run Kubernetes, how you run Postgres in Kubernetes, because a typical Postgres installation consists of multiple building blocks, multiple Kubernetes primitives. This is also not an exception. We have something that is called a stateful set that binds pods and volumes together. We have cron jobs for doing backups. We have config maps for storing Postgres configuration and scripts to bootstrap Postgres. We have secrets where we store some passwords or certificates. We also have a service that directs clients to the correct pod in case we have more than one. A stateful set actually allows you to scale your workload in a very easy way. You just increase the number of replicas, and suddenly you have another pod that runs identical software. Inside the pod, we have containers. One container is running Timescale, basically a Postgres instance with a Timescale extension. It is managed by Patroni, and we rely on Patroni to do high availability, to change Postgres configuration. We use some monitoring. We use it for monitoring, especially the fact that it can assign labels to the pod, like a row label, say, telling you whether the pod is a primary or a replica, or Postgres is not running at all. So this is basically typically every Postgres installation has something like that in Kubernetes, and you want to avoid writing this by hand. You can write this by hand. There will be 10 screens of YAML files, and you have to copy it and change everything if you want to run a new server. So typically people do templating. So you don't write YAML from scratch, but we pick a template and then you change something in that template, similar to what you have in Bash scripts. Helm is a popular solution for that. So you may run Helm to deploy instances, but it also has a lot of issues related to how do you react to changes of your original configuration. For instance, if you want to bump up shared memory and you change something in Helm and you redeploy, you typically just restart your container altogether. Helm doesn't know anything about subject domain. So it doesn't know how to operate Postgres. It doesn't know anything about how to restart Postgres in a proper way, how to change configuration. It doesn't know that if you want to, say, bump up max connections, you want to restart replica before the primary. So it's basically up to you. So people are writing software that implements this domain knowledge, and that software is called an operator. And there are multiple operators out there. There are ones from Crunchydata, one from Zalando, one from Enterprise DB, one from Postgres, and whatnot. There are quite a lot of them. And typically, if you want to run Postgres and Kubernetes, that is what you do. You take the operator, you get yourself familiar with how it works, with the format of the custom resource in the form of YAML, and then you start by creating your YAMLs and let the operator materialize them into the running Postgres instances. And then you change something in your YAML and see how the operator reconciles it and what does it do. We did not pick up any existing operators. We wrote our own because we have some specifics. In Timescale, we don't run only one Postgres instance for a service. We may run multiple because we have multi-node. So any stock operator is not good for that. We have our own operator and we have our own Timescale. We have our own Postgres custom resource, actually Timescale custom resource. Briefly, what is inside pod? Inside pod is a collection of containers. So here we have primary and replica. We run Patroni. Patroni manages Timescale. Patroni backs up WoW files to S3. That storage is used to create new replicas. That storage is used to recover existing pods if pods go, if a volume is corrupted. Typically in Kubernetes, if you bounce your pod, if you restart your pod, it will come again, pick up the same volume and run. So we don't need backups for that. But in case something happens with EBS or any other volume that you use to store your PG data, we rely on backups and continuous archiving to restore it. Actually use pgbuckrest for that. We also have another container that runs backups in pgbuckrest. It has a REST interface on top of pgbuckrest so that you can use a cron job, and the cron job pings pgbuckrest server. The cron job just runs some HTTP command, and the pgbuckrest has a Python web server, a very simple one that converts this HTTP request into the Python request, and then you have a backup. So we create backups, incremental backups every day, and full backups every week. And so far, they were pretty reliable, and we used it several times to recover an instance that went completely wrong. We also have config maps. Config maps contain Patroni configuration. We don't bake it into the Docker image because we want to change it pretty often. We also have some scripts. Patroni provides you a way to say, how do you bootstrap your Postgres? You can have a initdb, or you write a custom script that may either run an initdb or take some image from a snapshot or take some image from S3. All of this is supported, and we use that functionality. And we also put these custom scripts into the config map, exactly for the reason that we can change that custom scripts on the fly without bouncing the pod. Because we run customer instances, one of the problems that we have to solve is reduce the number of restarts of customer instances, of customer pods, because that means a restart means a downtime. Excuse me.
I have like a question again. This service connection, is it some connection pooler or like pgbouncer or something else? Or
Here we have a service, and the service is a node port actually. So we have a port on the node that directs you to the correct pod. Here you probably, here you can actually see. So this is the port that you're getting assigned, and then we use that port to direct you from outside.
There's no pooling there, right?
No, we don't provide pooling as part of the Timescale cloud yet, although we have plans for that. But nothing stops a customer from running a PG pool on their side.
Well, yeah, of course. But it will be one more. It should be like in the middle, and additional increase of round trip time will happen, right? If you don't run it. But okay.
It is.
Since you mentioned, since you mentioned downtime during restarts, if it's pgbouncer, it has pause resume capability to minimize downtime and basically avoid it, right? So do you have plans to improve in this area to allow zero downtime minor upgrades, for example?
The problem with pgbouncer is that this pause resume functionality works nicely when you have your workload in the transactional mode. I don't think it contributes a lot when you run pgbouncer in the session mode. So you have to have a matching workload, and we try to design our cloud so that it kind of is universal.
Right, but I see your point. I understand. Yeah, but transactional mode is better if you can afford it. If you don't have prepared steps.
Yeah, if you can afford it. The other problem with pgbouncer in the pause resume functionality is that you don't usually look at your database separately from your application. So what happens when you pause your database on a highly loaded service? Your highly loaded service starts to issue requests. Those requests are getting queued. That queue gets over the roof, and then suddenly you start to get timeouts from the application. So it helps you in some cases, but in many cases, this pause resume is
I agree with you
because you get timeouts on that side.
I agree with you. It accumulates connections, and we have only 32,000 ports, or like I mean TCP connections, and it's still like if we have heavily loaded service, it's quite quickly we can reach this limit, and it's a disaster itself.
Yeah, that's true. That is one thing. Another thing is if you're buying something on Amazon, and then your request takes, say, 3 minutes because someone decided to upgrade the database at that time, your client won't wait for 3 minutes. And Amazon won't wait for 3 minutes because that would be pointless. So it will give you a timeout.
It's a limited functionality, but for minor upgrades, when we need only a few seconds to restart, and if I agree with you, transaction mode is the thing. Yeah, okay.
Right. But we actually look at providing a connection pooler. We are not settled on exactly PG Bouncer, although we use it for some of the internal databases. But we think about providing a connection pooler on our side. As you said, the latency could be quite high, although the latency is not that different from latency from the client if you just connect PG Bouncer from your client side. But I think it would be very
PG Bouncer is on the same node as Postgres. But if it's in a separate node, it adds latency, especially different.
It does.
Right.
It does. But especially if you talk TCP, I think, instead of like Unix sockets.
About PostgreSQL, it would be so great to upgrade without downtime, right? Just click and forget, right? It would be great for users. Super cool.
Yeah, we actually, if you have replicas, you can do minor upgrades without downtimes, right? Because you
it's not the same.
Basically switch your clients and that's it.
Right, but some queries will be interrupted.
Indeed, yeah. But only for sub-second because you switch your primary when you upgraded your replica to the new minor version, and that is basically quite a few moments.
I saw a recipe with PostgreSQL to perform this switchover as well. So I mean, it'd be great not to lose any request, any connection. Of course, there is another approach. We repeat it all the time. Like applications should be ready to do retries. It should be designed for retries. This is much better, actually.
Always. If your application is designed for the case where your database is always available, please reconsider that, because Postgres is a very reliable database, but there are a lot of things where you want to restart your Postgres database to make sure that it runs for a long time without any issues. If you don't restart it, you may have much bigger issues if you just keep it running.
Much more than 50% of applications in the world are not designed for temporary downtimes. They don't do retries, unfortunately. This is my observation. Like only very limited number of projects and engineers follow this approach. So we keep repeating this. Do this. Yeah. This is important, right? So yeah. Okay. And then
let's move it forward. Okay. Yeah, let's move it forward. I don't want to spend too much of time. So this is the bigger picture. We have an operator. It packs things to S3. It reconciles running Postgres. Here we also have a deployment database. I know. Do you actually see my mouse when I'm doing like this? I just want to use it as a pointing device. So we have a database where we store all the state, and we have a separate service that is called the deployer. The task of that service is to create new manifests for our databases and to monitor the health of our existing fleet, reflecting that health in some metrics that comes to this deployment database. Particularly, we have some statuses like running, post, and in progress, and those statuses come exactly from the deployer and from this database. We use something that Kubernetes provides us. It is watches, an ability to subscribe to changes for any given object. And we subscribe to an endpoint, basically what powers a Kubernetes service, what is used to store IP addresses. And by subscribing to it, we immediately find out when Patroni declares a service that is not running as a primary, but it used to run as a primary, or when the service is not running altogether, because Patroni actually uses endpoints when it runs in a Kubernetes mode. And by watching those endpoints, we can immediately figure this out and put the new status in our database. We also use the database for monitoring. So that split is actually quite that split is actually quite good from the interoperability standpoint. We have an operator that just reconciles Kubernetes objects, and the operator is completely stateless. So it stores the status in the custom resource object, but it doesn't write or read from the database. And then we have a deployer that creates your manifests, your YAMLs describing your database. Deployer has permissions to do so. The operator cannot. So it has quite limited permissions. And the deployer also talks to the database and stores data in the database. So in case the database is not available, we still have our existing fleet running, being reconciled, and serving customer requests. It's only that the new deployments are affected. So we can do graceful degradation by trying to split our deployment into the Kubernetes part and into the kind of database and metrics part and house checks part. And as I said, Patroni is managing our Postgres. Patroni is awesome. It's a high availability solution written in Python. It basically keeps information about who is the primary and what are the members of the cluster in a consistency layer or distributed consistency system. It can use etcd, Zookeeper, console, or its own REST implementation. And it can also use Kubernetes, because Kubernetes is powered internally by etcd. When you change Kubernetes objects, this is also consistent. So we use that property in Patroni to actually write data directly as a metadata to Kubernetes. As I said, we use endpoints. There is a leader lock signifying who is the leader. When the leader disappears for whatever reason, could be high load, could be that it's not running anymore, or could be that it is partitioned. The lock that has a TTL is not updated, and then there is a leader race, and another node steps up and takes the leader role. So it's quite proven. I think a lot of companies are using it. Allows you to run custom scripts to do things like S3 recovery. And a good thing that it just completely runs in a pod. It doesn't have any dependencies on microservices, doesn't have a dependency on Kubernetes. So even if things go totally wrong, that particular cluster will be running without any issues, as again, it provides us some aspects of graceful degradation. I think I will skip that slide. Kubernetes advantages are great. We all know this. One thing that I want to stop is it provides you a way to do auto recovery even if you run only one pod. If your pod dies, a stateful set creates another pod exactly with the same address, exactly with the same volume. So your pod can just start and mount your volume. So if you want to save money on our system, you can run with only one pod. You will not get high availability, but you will get availability because we will recover, Kubernetes will recover your system if your pod dies. Challenges. So that's basically how we run our platform. And while we're running our platform, we found some things that Postgres has some assumptions. Kubernetes also has some assumptions. Those assumptions don't always match. And we found some mismatches. We found some things where Kubernetes could be improved. And we also found some things where we would like Postgres to be improved. That is specific to database as a service use case. So let's get the very first one. This is the out-of-memory killer. The out-of-memory killer is something that runs in a C group in a container. And when you are reaching the limit that is set on your container, so you say that I don't want to use more than 1 GB of memory. So what happens if you use more than 1 GB of memory? In a Linux system, this is configurable. You have a parameter that is called VM auto-commit memory, and that parameter could be set to always auto-commit, basically ask more memory that you have, hoping that you won't use it, which is quite fine for some applications written on Java or Ruby. For Postgres, it's recommended to set it to never overcommit, basically disallow asking for more memory that you have, because if Postgres Postgres handles this case, if you kind of try to get more memory that you have, Postgres will get you an error, And it will not put your server down. It will only terminate the process that asked for too much memory. Unfortunately, that parameter cannot be set individually per container. You can set it per host. And there are limited ways you can set it in Kubernetes, because typically on a single host, you don't only run your application containers, you run some side jobs, and those side jobs provide you a way of ensuring network connectivity or storing your logs. And those side jobs are not always written in languages that are compatible with these overcommit settings. So running as a node is possible, but you will be limited in what you can also put on the same node. That means there is also a long-standing issue in GitHub about that. So what happens if you set your overcommit memory to overcommit Kubernetes? If you exceed your limit on the on Postgres, if you exceed your limit on the container, then a special process comes that is called out-of-memory killer. And that process picks up a process in the system based on some scoring and based on some rating, typically the process that occupies, that takes more memory, and kills it with -9. And you probably know that you don't want to kill Postgres processes with -9. And specifically, you don't want to kill Postmaster, the process that manages all other Postgres processes, with -9, because then your queries are in limbo. They are running for some time, and then they found out that there is no Postmaster, we have to terminate, panic, and your server is completely down. And it takes time to recovery, because it will run through recovery, try to replay your WoW files, and it will be a major disruption to your application. So we don't want out-of-memory killer, but we want a process to get out of memory. Unfortunately, with Kubernetes, in a stock Kubernetes, this is not possible. This is the limits that you can set on the pods, and when you reach that limit, your process dies, your Postgres process dies, or just your pod dies, which is quite bad. What did we do about that? We designed our own library, and that library basically wraps around malloc. In Linux, there is an ability to do LD preload library, set this variable, and preload some library. And if you preload some library, it will shadow the implementation that is elsewhere. So we have our own malloc. We did not write it from scratch. We are not that crazy, but our malloc just calls a stock malloc while doing some accounting in the operating system. Essentially, it knows how much memory it can allocate based on the pod limits, discounting for shared buffers and some other memory, and then it can it collects requests coming from Postgres processes and sums them up. And if it finds out that the sum is greater than the limit, it just returns out of memory the same way as the stock malloc does. We did through a couple of iterations. Figuring out from the first iteration was a bit challenging. There are several issues. If you want to write that library, you probably want to know how things. You probably want to know C. You want to set up your debugging environment, and you want to give it a lot of time to test before you run this in production. But actually, right now it is running in production, and it works quite nicely. So we don't have pod being killed. That situations are quite rare, but instead customers just get out of memories. And as a bonus, we can have some alerts on that situation because that library also communicates with Kubernetes. It's written in C, and well, ideally, we want either Postgres to handle that case. I've been talking about that in Leipzig, PGConf DE this year in May. There were some threats on the hackers about improving Postgres, but there is no consensus on how do we want to improve it. And yeah, probably we want to continue that discussion. It would be nice if Kubernetes provides a sane way to either adjust Postgres processes score, basically excluding them from the possibility to be killed, or provide a way to set overcommit limit per C group, but we don't have control over Kubernetes, and that issue that I have listed, I think it is closed because of no responses or something like that. Maybe it will come, but maybe it will not come in the near future. Or if you want another possibility to provide memory allocation hooks so that you can write your custom extension that is called when you code plog from Postgres, and then it can do the same accounting, but not on the global system, but only on the Postgres level. This is, as I said, subject to discussion, and there is a threat on the hackers. So far, we just wrote our library that actually solves that problem. Another challenge, fewer downtimes. As I said, one of the goals that we have is to reduce the number of times that customer pods is down, especially when the customer is not aware of that. We have a concept of maintenance windows that is built into our services. So the customer can set when they want to perform maintenance. And from the operator standpoint, we respect that, and we don't do things that lead to the pod bounce during the maintenance window. However, we still, we not only run a cloud, but we also run Timescale extension. And we want our customers to use the latest Timescale extensions. They are compatible with each other. You can just install the new one and then say, for extension Timescale DB update, and it will be updated. And we want to provide the latest extension to our customers in the cloud. The problem is, if we were to use the traditional approach with Docker, we would have to build a new Docker image, and then we would have to restart all pods. And because we try to keep a fast pace of building new extensions and release several times, so once a month or something like that, it would be quite annoying to our customers. So instead, we adopted an approach of just shipping our libraries to the container. But we do this in a bit smarter way that just Docker, that just Kubernetes, kubectl CP, library name, and container location. We basically put those libraries on a persistent volume so that they are preserved during the restart. And we also symlink then those libraries from the persistent volume into the container. So when we are, excuse me, a bit of a long day, talking almost all day. So yeah, when you symlink those libraries, those symlinks are not writing anything that is already there. So we try to keep it as safe as possible. We don't want to overwrite libraries on a container that is being used. So we mostly just add new things there, like new version of Timescale extension or any other extension. This tool that we have, it's called HotForge. Well, Forge is the initial name of the cloud, and it runs at the container startup. And at the container startup, it creates all symlinks from the files on a persistent volume. And it is also available through the database interface. Because we are evil, we are owners of our cloud, and we can be evil, so we use copy to program to run that from the SQL interface. Now, that is not available to our customers, but this is available to us. And that way we can fetch you binaries without restarting a container by just using pSQL. We also have a CI/CD pipeline that builds those bundles. So if you are developing I will probably touch this in the developer experience, but if you develop your new version of the extension, you can use a CI/CD to put a new bundle to S3, and then immediately use HotForge to deliver that bundle to your running test instance and just test it in the cloud right away. This is how it basically, this is a diagram. This is a bundle, it's copied. This is basically a binary with some manifests. The manifests specify which Postgres version it's designed for, what are the files, what are the checksums. We don't want random binaries from the internet, as I said before. We want something that we verified to be coming from us. We ship it to the container, we symlink it, and then we basically call HotForge from the deploy process via copy to program. So we are very lucky that Postgres provides such a functionality. Use it.
It was designed for hackers mostly, but okay.
Yes, we are hackers. We hack our own systems.
Yeah.
You know, Postgres hackers is not hackers in terms of the black hats, but hackers in terms of people who use non-standard approaches to do things.
Name collision again. Okay.
Name collision again, exactly. So we use that. It's very convenient. We also have a possibility to just go to container, to exec into container and run it there. But a pSQL interface is very convenient if you just want to test something on your target system. I know that other people are doing similar things, like people from Postgres having something that a pod local operator that implements a similar pattern, although they wrapped it into the operator. We're also thinking about doing more automation on that. So far, it requires you to go into each instance separately. But nowadays, it works fine for us. So we can upgrade your extension right away. And then we also issue a Docker image. So all new instances will be running new Docker image with a new extension. Existing instances will be upgraded on the spot without a pod bounce, which is quite convenient to our customers. Of course, it would be nice if we could bounce individual containers in the pod without with changing a Docker image while leaving the other containers intact without the pod bounce, because pod bounce takes a couple of minutes and the restart of the containers takes seconds. Would be great if Kubernetes acknowledges that people are running databases there, not just stateless applications, and provide some mutable area. But that is not strictly necessary. We have our solution and other people are also using something like that. So the pattern is to break immutability of the pod, but not in the container file system, but in the site volume, and then use sim linking. And of course, copy to program. Copy to program is amazing. etcd. You have Kubernetes, and most Kubernetes production clusters are using etcd. And etcd is designed to be tolerant to faults, which means that you typically don't run a single etcd node, you run 5 or 7. And if you run 5, you can lose 2 of them without losing the cluster functionality. Unfortunately, if you lose more than 5, if you lose more than 2 and you run 5, it is really hard to restore it. And especially it's hard if you are doing this during the night and your server is down and your service is down. So we have to have runbooks, you have to test your runbooks, you have to do fire drills. And if you do this, etcd keeps surprising you with what could possibly go wrong and with some untested things that is inside Kubernetes that works that manages etcd, and with some very cryptic error messages that we have to fish your logs for. So not a fun experience. I've seen many times where etcd were down because of EBS burst balance. AWS allows you to run volumes with the performance higher than you have, and for a short amount of time. Typically, those are small volumes, and normally etcd data is not that high. So either you over-provision it and run several terabytes volume to store a couple of 100 megabytes of data, or you are coming into these burst balance issues if you suddenly issue a lot of logs, or if you have extra load on etcd, and then your etcd slows to a crawl, and then your etcd instances drop out of your cluster, and then suddenly nothing works. Why nothing works? Because Patroni depends on etcd. So there is a dependency that if etcd is down, Kubernetes API is down, Patroni cannot update the leader log, and your services cannot figure out which one of them is a leader, your instances in the service. So they'll go read-only. And this is a disruption to how design. One of the design goals of the control plane is, if control plane is down, keep all the services running. Obviously, Patroni provides great functionality, but it's also dependent on that on control plane in a bad way. If control plane is down, Patroni nodes goes read-only. And what can we do about it? Those slides are from May. Right now, fortunately, there are good changes in the Patroni core. But in May, we had to do some fire drills. We had to test things on ephemeral clusters. We had to write runbooks to limited success, so to say. And we also had a solution. Say we only run one pod. We know that this pod is a primary. We know that there is no replicas. So we have a very small changes in Patroni, in the fork of Patroni, that says there is a static primary. The static primary says this is a primary, it's static, it's only one. If Kubernetes API disappears, this node keeps running. It doesn't need a failover. You can ask, why do we need Patroni?
It doesn't need Patroni, right?
It doesn't need Patroni, but you typically want to manage your services in a uniform way if you have hundreds of those. And some of those have replicas and some of those need Patroni, some of others not. So we need Patroni for things that are that are beyond failover. We need Patroni to store configuration, to label our pods, and many other things. So we just adopted to run without API being available. Luckily, there are developments in Patroni core in the stock Patroni made by Oleksii Kliukin. He has an amazing feature that is currently in a pull request, and I encourage people who use Patroni to just go there and test that, because you probably came to the problem of your DCS is not available and your clusters are read-only more than once, even if you don't use Kubernetes, if you just use etcd. So there is a mode that is a fail-safe mode, and this fail-safe mode, Patroni can continue running without access to DCS if under certain conditions, and those conditions are you have all your cluster members intact. This fail-safe mode is turned on, and the primary can connect to every replica, and every replica responds to the primary. So if that is satisfied, it basically you run your cluster normally, then your primary keeps running and it keeps serving write queries. So that completely obsoletes the hug that we had with the static primary. It's still in a pull request, so as I said, if you are interested, please go there and test things or to the review. And we are going to transition to the fail-safe mode in the future. Well, there is a wish list, of course. We want etcd to be more reliable, not actually more reliable, but more observable. If it's down, we want to have some documentation which says, well, how to recover it without doing dump restore. What are the things that we have to look at? Yeah, Patroni isolated mode. Luckily, that part of the wish list is Dreams control. I have mentioned that you have multiple layers. There is Docker, AWS, and Kubernetes, and you have to work around some bugs. We had a bug with the container file system. Sometimes for encrypted EBS volumes, that bug came from AWS. Those volumes pose themselves as already partitioned with Atari partition. This is Atari. It's a gaming computer from 80s. Oh, yeah, it says 85 here. So long ago, it doesn't run Kubernetes in any shape or form. But Kubernetes recognizes there is a file system, and yeah, Atari file system, why not? And just put it stuck at startup. So we had to work around that, and we worked around that by using snapshots. We took a very small volume, 1 gigabyte volume, and then when we create a new instance, we just took that snapshot, created a volume from that snapshot, and extended it. We also had to run a init container to extend the file system, because Kubernetes can extend a volume, but file system will stay with the original site. Luckily, init container can fix it, and also luckily, AWS already fixed it, so you have to do nothing. And we actually tore down that hack, but I still kept it because I want to illustrate that you will come into bugs not just from Kubernetes, but from Postgres, from Docker, and from your vendor, which is AWS, and you have to be prepared for that. So yeah, right now problem solved. So another part of my wish list satisfied. I'm very happy. Volume size increase because you run your data, and your data is typically increasing, especially in the time series workload. You basically add your data on top of existing one, and your volume grows, and suddenly your volume grows to the size that is higher than your anticipated, and you have to resize the volume. And then you come to AWS specifics, which is you can only resize the volume. First thing is that we don't want you to resize your volume manually. So we designed a service that is called Autoscaler. The Autoscaler looks at your growth of data growth, looks at your volume size, looks at how big you want this volume to grow at the end of the day, because you also pay for the volume, so you don't want it to grow infinitely. And then we use that Autoscaler to grow your volume. That is kind of solves some of our problems. except for the fact that in Amazon, you can only grow your volume every 6 hours. And if you need to grow it twice over these 6 hours, you are out of luck. So also when the data is compressed, you don't use the original size, but you may use 10 times less size than you have, and you don't want to pay for a bigger volume. So how do we solve it? We cannot solve the Amazon limit, but we provided a way to fork your service. A fork is basically a clone, a copy of your service that is provisioned from S3 using Patroni using Patroni custom bootstrap scripts. And we use the fact that we do continuous flow archiving. So you basically provision it to the point where the fork has been requested. We use recovery target name to avoid fork starvation. That is, if you have a very intensive write load, we don't want your fork to start indefinitely long. So we kind of set a cutoff point at the point where you command to create this fork. So we use pgcrest, we use Patroni together, and we have forks. The forks can have different resources from the primaries, and that partially solves the problem of how do I scale my volume if 6 hours has already passed, or how do I make sure I don't pay for the volume that is not adequate for my needs because I compressed all the data. There are, of course, some downsides to that forks because it's a point-in-time fork. We are working on providing continuous forks, which will follow your work stream until you manually say that you have to detach it from your primary, and that we will solve some
basically
use cases.
It's standby using restore command, getting walls from the archive. It's just replica, right? How? Maybe I'm missing something. Why it has name fork, not just replica in this case?
Because you typically do not detach your replica from your primary. You typically promote your replica if you want to switch over to it.
Right.
Or you typically use your replica for balancing your read queries. But
Right.
the fork is designed to be a separate service.
Right.
One thing that we have in Timescale Cloud, because we use stateful sets, the replica is identical to the primary. That is not a bad thing because you typically want the promoted service to be equal to the primary. I have some horror stories from one of my previous jobs when we wanted to spend money. We wanted to save money and had a very tiny replica. And then we found out that we promoted to it, and then our production database is suddenly running on almost like a piece of paper.
Okay.
So you want your replica to be equal to the primary. The fork does not have this limitation. The fork is a completely different service that just starts off not from initdb but from Stream.
But we have like already. Like I mean, there are many terms, and it's all so confusing. For example, RDS uses, of course, replica, but if you promote it, it's named like a clone, right? It clone at some point, but it lives its own life then because it's a primary as well. But you use fork, and some people use branching already, and this is very confusing. I think we will continue discussing this discussion in Berlin at pgconf.eu. I propose this.
Yeah,
because
I don't mind good names, but naming things enough by one is the cursed problems of computer science. So it might be not that easy.
I agree. Yeah.
I'm going to the end of this, so bear with me for a couple of like 5 or 10 minutes. I don't know if we have that time. I can do it faster, but this is specific to running a managed service. If you run this on premises, if you fully control your database as a service, you trust your users, and everything is fully kind of in sandbox environment. You can just give them super users, and that is fine. That is what we did at Zalando. If you are providing a commercial service, you probably don't want to give super users to people, because one thing that they can do is to use the database in a way that put it down and you would have to restore it in a very complicated way because super user can do anything. More importantly, they can escape your Postgres and then can go into a container, and then they can maybe escape further if there is a vulnerability in, say, Kubernetes, or if there is a vulnerability in in the Linux file system or in the C group implementation. I think there was a recent report from some hackers that managed to do this on Azure and used, I think, something like copy to program to escape a container and go further and explore the infrastructure. I'm not sure this is Azure, but I think this is one of the major clouds. So you want to provide admin access, which is a user that can create tables and do a lot of things, but you don't want to give super users. You also want this user to be able to create other roles, but this create role is also very dangerous because you can assign basically any role to any user except for the super user. But you can assign a role that can run copy to program, and then that role can become a super user by, for instance, changing your PGHBA inside the file system, and then restarting your Postgres, and then suddenly you allow unauthenticated access from the super user, and you are hacked. So we want to limit which roles this user can do, and we want to limit some other things that this user can do. So we created an extension that is basically a planner hook, and that extension, an executor hook, not the planner hook. And that extension actually intercepts some dangerous commands like create role and validates them against the roles that we have. And this allows some commands that would lead to a user, say, escaping a container or getting super user. Also, we don't allow changes in configuration parameters. Yeah, basically, this shows the possible exploit. And in our environment, we have an extension that just says that you don't have sufficient permissions for that. So it catches that command and says only super user is allowed to do that. We also don't allow installing arbitrary extensions by a non-super user. This is also not safe because an extension can do whatever. Some extensions can do things that will escape from the Postgres, from running Postgres. So we use a pgx whitelist, an extension from Dimitri Fontaine, one of the prominent community members. And we set a list of extensions that we trust, and we only allow installing that extensions, basically only vetted ones. There is a similar functionality in Postgres 13 that is basically trusted extensions. But in pgxw list, we also can run arbitrary sequels before you install extension and after you install extension. So we take extra precautions to make sure that when you install your extensions, you, for instance, don't mask your public schema with some other schema that you created by yourself, and then you installed some operators in that schema. And then those operators could be called instead of calling the public schema. And then suddenly you just execute arbitrary code with super user permissions. So we don't want that. And we use that post and pre-install hooks to sanitize things. And we have a vulnerability checker that allows you to look for those problems in your own databases. It is called pgspot. You can get it on GitHub and you can run it against your own instances.
Yeah, that's super useful. An extension you mentioned before, it's internal tool. You haven't published it, right? Okay.
Yeah, we don't publish some of that extensions. It's currently internal. We, in principle, don't mind publishing it, but that it's a bit complicated. It takes some time to whitelist and so on. Yeah, so but that is open source, and both pgx whitelist, thanks to Dimitri Fontaine, and pgspot, thanks to Sven Clem from Timescale, they are open source. Well, obviously, that thing is like kind of a minesweeper. We found some issues. There could be some issues we did not find. So this is always like, how many mines can you get there? We want, ideally, Postgres should provide a way to avoid super user altogether. We just want fine-grained permissions, and if you want to give some but not all permissions, we just omit some of those. Super user is too powerful. Unfortunately, there are cases where you cannot omit running super user altogether. So last part, developer experience. How do we develop things? We have operator, we have deployer, as I described it, we have a Docker image, and say we roll out a new feature of the operator. How do we make sure that this rollout will not disrupt customer data? Because if an operator has a bug, that operator may decide, for instance, to delete the cluster or to delete some of the components of the cluster, and suddenly the cluster is not available. Sorry, the service. the Postgres database. So we use Kubernetes, the idea that each namespace or each object in Kubernetes could be labeled. And we specifically use namespaces to host customer data. So each namespace in Kubernetes hosts multiple pods that belongs to a single customer. We call this a namespace a project. And those projects are labeled. And we basically label them with the, here we label them with colors. In practice, we label them with more meaningful names. But basically, we can label a namespace with red, and then we say, this operator will only act on red instances. And that means that we can partition all our databases and deploy the operator that only touches parts of our fleet or touches only the zone that is used to run only our internal data from timescalers. So we are still running this in production environment, and we do have staging. So we first test things on staging before coming to production. But even for production, we can run things in a production environment completely, but limiting the scope of what we are doing to only certain clusters using labels. And we can relabel those zones quite transparently without interrupting customer interruptions. So we can always designate which of our services receive this feature before others. And once the feature is completely stable and we know that we can trust it, we deploy it gradually to all other zones. And that way we can both avoid unplanned downtimes and have a fast pace of deployment by introducing features to production in a kind of right when we think they are finished, without kind of complex 2 weeks process of vetting this and testing this and retesting it. And for most of our services, we also have out of cluster development mode. Sometimes you want to run this on your local laptop. You have a service, you can run it in the pod, but debugging things in the pod are tricky, particularly because we don't have privileged containers. We did a conscious decision to run things as an unprivileged pod to avoid blast radius if things are getting exploded from the Postgres perspective. So we run things as unprivileged containers, and that hinders some debugging inside the container. We can always go to the node, but that is tricky and complicated. So we allow you to run your services, to run services of the developers, either the operator or the deployer, on your local laptop, connecting to Kubernetes, to the development Kubernetes cluster, running actual services. You run your service, you run your database locally in case of the deployer, and then you develop. You can use a profiler, you can use a debugger to test things, and that allows you to also do a fast-paced development while still talking to AWS, while still talking to the environment that is close to production. We also provide a way to run things in kind, in Docker on your local system. If you want to develop things that way, if you want to start testing with your local system and only then transition into AWS, this is possible. However, kind is quite limited. It's hard to figure out what is inside unless you also deploy a management stack there, which is tricky. You have to support running it locally, set the limits and requests in a reasonable way. It doesn't much one-to-one to what we run in production. We typically have some version drift with kind. You cannot test AWS specific features. If you do volume resize, this kind will out of luck because kind just gives you the local volume backed by directories. And yeah, some non-cloud dependent features that are easy to test, like bootstrap scripts, are easy to do with kind, so we still use it from time to time. And yeah, that's, I think, one of the last slides. So the rest, we have deployer tests. We have unit tests and the operator of the deployer. The operator does testing using we actually create a Kubernetes cluster and actually roll things there and create real services to test it. Deployer also runs with real database. We don't mock a database. We have a way of running production query. We have a way of running queries there. We have text for Docker image to make sure that the extensions we pack in the Docker image are those extensions that we want to pack and that we label it correctly. We have a dedicated development environment. We have CI/CD pipeline that runs those tests continuously. We are working, at some point we could span an ephemeral cluster with just a few commands. If you want to test something like what happens if my etcd dies, Right now, we are working on improving those features, so we can use it also in CI/CD pipeline. So it's a bit of progress. We do tracing between microservices. We centralize log collection, so we can correlate issues with multiple Postgres instances. We have usual suspects of graphing things, alerting. And in the operator, we have a hands-off mode. The operator does constant reconciles, but we can turn it off if we just want to hack things locally. Say we want to change a script on my test instance before doing this in production, or we want to do a hotfix. We disable the operator reconcile, we change that script, we look at the results, and if the results satisfy us, then we do changes in Git and then route out. So we can disable the reconciliation of the operator while still keeping the cluster running. That is very important. If you want to develop things in Kubernetes, make sure that you have most of those, because otherwise developing things there will be tricky, much trickier than if you do this in a local environment. That is all the slides for now. And I want to thank you very much for having me and for getting to the end. I know we are out of time, but yeah, I'm very happy to answer.
Thank you.
I'm very happy to answer any questions that may arise.
I have a couple of questions. And first of all, it's a lot of info. And I know like many people build their own clouds right now. And you shared a lot of very interesting things. It's like interesting, not only about Kubernetes, but how to build cloud and so on. Very interesting. And I actually also learned what we can use in our stuff, although we don't build cloud right now. So before I ask a couple of questions, I need to, like we discussed this glibc the problem. And today Postgres 15 RC1 released actually. And there's a plan to release final actual Postgres 15 version in a couple of weeks. And I've checked release notes, and it has from Peter Eisentraut, it has record and check collation for each database. So there will be protection from such kind of painful problems in Postgres 15. This is good. And like, I mean, container, it's not a problem of container, of course, it's a problem of Postgres, and it's kind of fixed. Yeah. So this is one thing, and a couple of questions. First, you discussed replication, everything like as usual, but I wonder, do you have some use of logical replication or some plans of using it in Timescale Cloud? All that you try to avoid it because it has limitation as well.
We looked at logical replication for some use cases, particularly doing migrations from other systems.
Right.
But right now, it's hard to run it. It's not safe fire and forget thing, if I may put it this way. You have to babysit it, especially for big databases. There are a couple of issues with logical replication in practice. One is that typically you write your data from many backends at once in your publisher, but then on the subscriber, you replay your woes with only one process. And that is an imbalance that leads to the subscriber being far behind the publisher on heavily loaded databases. So depending on your workload,
especially if some indexes are missed, right? Some indexes are missed on subscriber, and yeah, it's slow.
Exactly. And also you have to populate your subscriber, and then your publisher with the schema and so on. So typically, and with initial data, so typically, how do you speed that up? You disable delete your indexes. The problem is it doesn't work if you don't have primary keys. So it works, but it's very inefficient.
There is a recipe how to convert physical replica to logical replica. It's quite easy.
You could.
Yeah.
You could probably.
If you need everything,
do this.
It's not always. Sometimes you need just some part of database, several tables. But if you need everything, for example, for upgrades we need everything. You can convert physical replica to logical replica quite easy, right?
Yeah, you could kind of assure the initial dump, but then you have to figure out what is the position of your WoW files that you have to start replaying from.
This recipe is known for a while, for several years, but recently we reproduced it as well. So you just use recovery target LSN. You create a slot, LSN, then you use it,
and you use that,
and that's it. It pauses, and then you just promote it and use it as logical replica. Quite easy.
Yeah.
We already there is
that is
ready to mine.
that is good, but if you do migrations, for instance, from any other or from any cloud provider, you normally do not get a physical replica. You don't get physical replication because of a lot of other
for
things.
these kind of migrations, word migration is also overused everywhere. Database migrations, migration from
naming
Oracle.
things is hard.
Yeah, but for upgrades, for example, for major upgrades, I think.
Major upgrades could be done with the logical replication, but for big and high velocity databases, in my experience, it's much less hassle to just set a downtime for several minutes while you are doing your siblinking of dump restoring siblinking of files. And it takes some time to restore the statistics. So this is a problem that could be solved, but not solved yet. But it's much more reliable than relying on logical replication. And while this is possible, it's subject to all these problems with the velocity of data changes, and your replica may go behind your primary forever because it just cannot keep up because it's only one process that restores data. Also, logical replication does not support DDOs, so you have to be careful. So you have basically, if you want to use logical replication, the best scenario where you completely control your primary, your subscriber, your publisher and subscriber. You absolutely know what you're doing. You vetted your queries. You tested things somewhere to know that your load is adequate for that. And you absolutely, totally cannot stop your database even for a couple of minutes. It's a very exotic use case, I would say. Not unheard of, but most customers do not have that problem. And we are working on doing major upgrades, but that would be based on PG upgrade.
PG upgrade -k, right? With Symlinks.
Yeah, PG upgrade -k.
Harlinks actually. Right.
Yeah, I find some people who don't trust PG upgrade yet. They do dump restores, but we do trust PG upgrade. Over my experience at Zalando, at Adjust, and other companies, I think PG upgrade is pretty solid. I haven't seen any issues that are rising from PG upgrade itself, although there were some bug reports, but they are fixed promptly.
It had some bugs, but fixed.
It does. It does. It did have some bugs, but they are fixed.
Small complex details. So everything in general works, but sometimes it doesn't.
Okay, different question.
The problem I wanted to say is that the same could be attributed to the logical replication. It works most of the time, but you see that most of the time might be not good enough if you want to provide database as a service, because even when it doesn't work for some workloads, those some workloads could be hundreds and thousands. Oh,
right. I stopped it because we finished and we finished just to see your big picture of you. So thank you for response. I agree with almost everything, but still sometimes even 10 minutes would be good to eliminate. Okay, but I agree. What about different thing? You mentioned this thing that is called forking in your case. Provisioning a copy of data from archive and even keeping it as a folder for some time, right? Do you see some demand in the area of provisioning of non-production environments, like developers need to build some staging or something, and they need to bring production data, then maybe remove personal data from it because of GDPR and so on and so on. You see it, right?
There are a couple of use cases for forking, and one of these that you described is quite prominent. You want to have a development instance, or you want to have an instance that has an exact copy of your production to run some queries. And that is one of the use cases. Other use cases are
to check index ID, for example, right?
You basically can do whatever data changes on that fork. The other test is the other thing is you want to do the point-in-time recovery, for instance. You don't want to do this on a primary. You want first to do this on a replica. For instance, you dropped your data, you dropped your table. You don't want to roll out your primary. You want to create a fork, do the point-in-time recovery on the fork. salvage that table that you dropped and then move it to the primary. So that is kind of a data recovery. That is the second use case of forking. And I think those use cases are quite well supported by our current approach, but we are looking to speed it up. So we are actively exploring using AWS snapshots instead of using WoW recovery. One thing
Patching
that it gives
PG
us.
data with pgback REST. Yeah. This is replacing this initial step by restoring from snapshots. It takes only a couple of minutes.
Yeah. There are two things that it gives us. First is it provides a much faster experience when restoring data compared to recovering WoW files, because also recovering WoW files is a single process that takes them sequentially and loads them. It's faster when you use something like pgback REST that can copy files in bulk instead of doing this one by one. But still, the recovery is a contention point for huge databases when you have a lot of WoW files. You can always do backups more often, but you are just delaying this problem. You cannot evade it. And for snapshots, we can reduce that time to recover WoW files to minutes because we can do very, very frequent snapshots. They are incremental and they are very fast to restore.
Don't you think that pgback REST itself should support it, like work with several big cloud providers and get initial PG data faster, get more walls faster, and so on?
That would be amazing.
Yeah, I also think it, but when I talk to pgback REST developers and WoLG developers, I don't see they understand this request. I don't know why. Maybe I don't understand something. I always accept the chance that I don't understand some problems. Okay, so
to be fair, pgback REST is open source, so if you want some new functionality, we have to work on it.
Right, I agree. But I agree. This is fair. And a little bit different question. Since timescale support, like basically sharding, it's not called distributed timescale, right? Multiple nodes are used to the data is split to multiple nodes physically, and this is a great feature. But what do you think? Since this is my topic, to build proper, very fast, very robust non-production environments, but problem, we only have requests, we don't have solution. I wanted your opinion. For example, we want to create an exact copy of environment of production for testing and various tasks. But what to do with synchronization of the state of multiple different nodes? Like how to synchronize them, because if we don't care about it, they will be unsynchronized and the application will find some inconsistencies, right?
This is indeed a hard problem, and what we do at Timescale is provide a kind of distributed restore point. So data nodes are not replicas; they are independent Postgres clusters. They are just tied together by the extension. And if we want to have a distributed restore point, we just issue that command, and it will create the restore point on all nodes at the same time.
Regardless of timeline and LSN, because they have their own timelines and LSNs, right? So we cannot from a timeline and LSN we cannot understand. Right.
They are completely independent. They are completely independent. So we create this restore point. It's kind of a name that is in the WoW stream of every node.
It's Postgres functionality restore point, right? So
it's Postgres functionality, but we make sure that this is synchronized. So we don't create the restore point where, say, you have one node in one state, another node in another state, because they kind of a single transaction can verify several nodes. And we kind of want those nodes to be in sync. And also, I'm sorry, I'm not very knowledgeable on the details how it works. It's a team that designs Timescale extension itself. So I only know.
But basically, there's something that allows restoring Timescale cluster to clone it in good form. This is interesting.
Yes, you can restore them in a consistent way. So you may not restore all the data that you had, because that is not in the restore point, so that is past the restore point. But you can recover it to the point where it's consistent. So if you
Great.
don't
This
have
is
data
super
that is
interesting.
unaccounted.
I will look at it. It's interesting. Yeah.
Yeah.
Okay.
Yeah.
No more questions. Maybe Ilya has some questions about Kubernetes and Postgres and Timescale. If not,
I would probably ask then the last question. So, like 10 years ago, then people are speaking about Postgres and any containers. Actually, many was complaining that, okay, that's a good thing to investigate, but it's different. If you need a serious workload, you need to use your bare metal server or cloud or whatever, but not Docker. Like a couple of years ago, people starting to tell, doesn't change anything. Basically, database in container is the same. So, what's your attitude now towards this thing? Is Postgres in container the same experience like Postgres on bare metal, or still there are many differences?
I think it's a better experience than Postgres in a bare metal.
Okay.
And many people complain about or think that it will be a performance issue of running databases in a container. But the actual performance changes are in several percents of the CPU. And you're basically typically not bound by CPU when you run your databases. So I think containers are there and they are ready for really big databases, terabyte-sized databases. And they provide a way of kind of packing the binaries and shipping them and making sure they are the same, which is a huge problem on premises. If you have multiple servers managed by Ansible or Puppet or whatever else, and you want to keep these Postgres in sync, then you always find some outliers that does not behave like the others, and your script runs almost anywhere, but not on that server, and suddenly that version drift, and you have a problem, you have a bug in the old Postgres version that you find in half a year, and nothing works. Containers does not do this, or at least if you have a old container, you can immediately spot this by just looking at the image. So I think containers are ready for prime time, and they are used by, I think, by most of the major cloud providers and by many companies. If you have any doubts about using containers or not, you can just always use it on your laptop and see how it works before running production. So there's no magic, no mystery, and nothing that you won't be able to observe.
good. Thank you so much. Thank you, everyone who watched this. Please ask questions in the comment section. We will be monitoring, and subscribe and share, and see you next time. Thank you. Bye-bye.